Yes, it's about percent composition, right? Percent composition. So percent composition refers as chemical formulas that are used to represent the elemental makeup of a compound. How much that each element makeup of the compound would be calculated quantitatively by percent composition. So the percent composition for a compound is the percent by mass of each element in the compound. So here is an example for you. What is the formula mass of ammonia? Formula mass of ammonia, NH3. To find out the formula mass, I didn't like the word formula mass. It's supposed to be molecular mass because this is NH3. NH3 is not ionic compound. We use the word formula mass for ionic compound, not for covalent compound. Okay, so they should supposed to say what is the molecular mass instead. Molecular mass. Okay, so just you can make correction for yourself to the molecular mass of ammonia. So from here we can see that we have nitrogen. We have 1 atoms of nitrogen. That's 14.01 AMU. Whereas we have 3 hydrogen atoms, that's going to be 3 times 1.008 AMU. So altogether, the molecular mass or the molecular weight for ammonia is 17.03 AMU. Okay, so that's not a big issue here. Now, the next point is that what percentage of an ammonia sample is nitrogen? What is the percentage of nitrogen in ammonia? So that we have to calculate the weight of nitrogen divided by the molecular weight of the entire compound by 100. That's percent. Okay, so 82.27% composed from nitrogen atom, whereas 17.76% composed from hydrogen. That's how we calculate percent composition. You see, I'm sure that we can have more examples regarding with these. Okay, so here, for example, in the previous section, the molecular mass of aspirin was calculated. What is the percent composition of aspirin? Okay, so this is going to be a practice problem for all of us. So the formula for aspirin is going to be I can give you I can able to write the formula. Oh, hold on, let me write the formula for aspirin. Aspirin has let me see if I can able to write somewhere here, C9H8O4. Okay, that's the formula for aspirin. Okay, so based from this, what I want you to do is that we're going to calculate the percent composition of carbon, right? Percent of carbon, percent of hydrogen, and percent of oxygen. Okay, so the way how we do this, okay, first we need to find out the molecular weight of aspirin. So the molecular weight of aspirin, can anybody tell me what is the molecular weight of aspirin?
180.15.
It's right here, 180.15, right? So the percent of carbon would be the mass of carbon, which is going to be 108.9 divided by 180.15 times 100.
Okay. It's actually 108.09.
What? 108.09, yeah. Oh. Okay, thank you, Marcus, for the correction. You're right, sir. 108.09 divided by 180.15 times 100. So I want you to do the calculation so you can give me the answer, okay? So
60%.
Who?
60%.
60?
Yeah, 60.
Okay, thank you very much, 60%. We can do the same for hydrogen. So what is the setup here for if you want to calculate the percent composition for hydrogen? The setup is going to be what? is going to be the mass of hydrogen is 8.064 divided by 180.15 times 100, right? That would be the percent for hydrogen. Again, let's do the calculation and you can give me the answer. If anybody had the answer, let me know. In other words, what you have to do is you divide 8.064 divided by the entire molecular mass of aspirin, which is 180.15, and then you multiply that by 100.
You're using more significant figures right now.
4.476.
Yeah, I would say 4.48. Okay, you can round it up, 4.48. Does that make sense?
Yes.
Okay, so we can do for oxygen. So what is the setup? Can anybody lead with this, with the last one, the setup? How do we calculate the percent for oxygen? We take the mass of oxygen. Yeah, can I have someone? I'm sorry.
6.00.
Okay, 64.00 divided by
180.15.
180.15, yes.
Times 100.
Yeah. So that's going to be the percentage composition of oxygen in aspirin. So when you do that, what will be the numbers that you get?
You get 35.53.
Say one more time, please.
35.53%.
35.53%. Okay. Yes. So that's how we do the calculation. Okay. So that's how we determine the percent composition. If anybody has any question, please let me know. If not, then I'm going to move to the next slide.
Quick question, Professor.
Yes, sir.
So when we rounded the 4.48 figure, that put us at a point where when you added the 35.53, our percentage went over 100%. Our percentage went up to, I think, 100.01%.
Yeah.
Is that okay?
Yes, that's okay. When you add them up, theoretically, you should get 100%, but sometimes there's always a couple of significant figures will be there, but it should be, I didn't add them up, Marcus, but I can tell you from the top of my head, it's supposed to be 100%.
Okay. In this case, it wasn't. That's what I was asking.
Is it 100%? Did you add?
Is it not 100% because we rounded up the 4.8% and the 35.53%, Professor?
Right. So if we round it up, the technicality is that when you do the percentage composition, let's say that you have aspirin, right? This is something called a qualitative analysis. In other words, aspirin has carbon, hydrogen, and oxygen, which is 9 atoms of carbon, 8 atoms of hydrogen, 4 atoms of oxygen. That brings you together 100%, which means there is no any foreign element there. If you get 99.9% or if you get 100.01%, you are fine. You don't have any other foreign substance there. If you add them up, the percentage composition, let's say you get 92%, you have to be very careful. There is some foreign element there which holds 8% of aspirin. That is risk, that's a big risk. But if you are rounded up to 99.9 or 100.15, that's still clean. That's, you have only the component of carbon, hydrogen, and oxygen. Okay, so 99.9 or 100.015 or 100 point something considered as 100%. I didn't add them up like you did, Brittany or Marcus, but I'm assuming that you are very much close to 100%. That was my thought, actually.
Yes, Professor. I just wanted to make sure. Thank you for that explanation.
Okay, you're welcome. You're welcome. Okay. Okay, so I'm going to move to, let's see. Here. Okay, this is a practice work for you. Here. Amethyst is a purple form of quartz, SiO2. I'm sure that those of you who collect minerals, you might see this in the market, in the mineral markets. You know, somewhere in Timonium, there's the Amish market. I sometimes go there. They have a very nice show there, mineral show. So amethyst, I bought one from I like collecting minerals. So amethyst is SiO2. Now, the color comes from the composition of manganese and iron. There's some components of manganese and iron, not too much, but that purple color is having manganese and iron will bring you this color. But pure amethyst is the formula is SiO2. Okay, so amethyst gets its purple color from a tiny amount. You see, tiny amount, so not too much. A tiny amount of iron and manganese brings the color of amethyst, the color of quartz. It's called quartz, by the way, SiO2, into purple color. Okay, having said that, what is the percent by mass of silicon in amethyst? We need to calculate the percent by mass of silicon. What's the percent of by mass of oxygen in amethyst? And the last one, if you wanted to obtain 250.0 grams of silicon, how much amethyst would you need? So this is something that I want everybody to think about it. Maybe I can give you a couple of minutes, 3 to 5 minutes, and then 5 to minutes, something like that, and then we can discuss, okay? Now, so you need to find the weight of silicon, the atomic weight of silicon, the atomic weight of oxygen. And just for curiosity, how many of you have a periodic table with you right now? If you have a periodic table, you really don't have any problem to calculate the weights of, I see only 2 people here. I see Brittany, Marcus, it's amazing. Emily, thank you very much. And Miriam, Sebatu, thank you. You need to have a periodic table, okay? We're not going to discuss about Marilyn. Okay, thanks very much. Okay, Brittany, can you please tell us what's the weight of silicon so that everybody can able to do the calculation? If you, Brittany or anybody, Marcus or Marilyn, can you please give us a weight of silicon from the periodic table?
32.059.
32.059 AMU. Thank you very much. And oxygen is about 15.99. Am I right?
Yes, 15.999. Yes.
Okay, but my periodic table says that silicon is 28.085.
Yeah.
Oh, wait a minute. Silicon is what?
28.085.
Okay, what do you think, Brittany? Okay, hold on. I don't have. I want to be honest with you. I can bring a periodic table, but it's in the back.
Oh no, Professor, they're correct. It's 28.1. I was looking at the wrong element. My apologies.
Thank you, Mark. Thank you for the correction. 28 point what, Marcus?
28.085.
085 MU. Okay, you have the weight of silicon, you have the weight of oxygen. So I want you to do A, B, and C. Weights are given here, and then we can move on.
All right, so can I go through the steps?
I'm sorry?
I said, can I go through the steps real quick?
Yeah, sure. Yeah, yes, sir. Okay.
So first we have to determine the molar mass. Okay. And to do that, we have to multiply oxygen times 2 because we have 2 oxygen atoms. Mm-hmm. So we'll have our 28.085 for the silicon plus 15. Get my calculator. Mm-hmm. 28.085 for the silicon plus 15.999 times 2 for the oxygen. Mm-hmm. So our total molar mass is 60.083.
60.083 MU. Okay.
All right. Once we have that, we can just divide 28.085 by 60.083 to get the percentage of silicon, which is 46. How many significant figures are we using right now? 5? No, 4.
It'd be 46.74%, Marcus.
Yeah.
Right.
Let's do 4 significant figure actually, because I
Okay.
oxygen as 15.99. Okay.
Okay, so 46.74% for silicon.
Okay, that's for silicon. Okay, how about for oxygen?
So for the oxygen, we just
Let me
take
write.
our 15.99, multiply it times 2. That's
Wait.
31.98 divided by 60.083.
Slowly,
That'll,
Marcus. I have to write what you say. For
oh, sorry. So
go ahead.
I'll take the 15.99 and multiply it times 2 to find out how much oxygen we have. So that's 31.98 AMU of oxygen in the total 60.083.
Okay. Times 100%, right?
Right. So that gives us 53.22%.
It seems right to me.
I got 53.26. Marcus, I think you messed up when you didn't do the 3 significant figures for oxygen.
Yeah,
it should be 31.998 divided by 60.083, and you'll get 53.26. And that plus the 46.74 gives you 100 exact.
All right. Yeah, you're right. So, Professor, just now when I did it, I used 15.99 for oxygen. I should have used 15.999. In my periodic table, it has 5 significant figures for oxygen.
I would go with 4. I would go with 15.99.
Okay.
Yeah. So it's pretty much close, but but you understand the concept. That's okay. In some cases, value will be given to you. So I think Brittany also took maybe 15.99 to 4 significant figure. That might be the reason that you may get 53.26. I didn't make the calculation. I'm just comparing your answers with the number of significant figures that you took might make that slight difference, but the concept is that the interested element has to be on the top divided by the entire molecular weight.
Okay.
So that's how we do. Now, we do the first part, second part. If anybody has any question, please raise your hand and I can able to answer, or these guys will answer your questions as well. So we still have one more question left. If you wanted to obtain 250.0 grams of silicon, how much amethyst would you need? So how would we able to solve this problem?
This is the part I always forget because we have to convert.
Wouldn't you take the 60 point, give me 1 second, Professor, 15.999 plus 28.
It was 60.083.
I'm sorry?
Yes, so when you take this 60.083 and divide that by the 250 grams.
Okay, divide by 2 like this?
I think it's the other way.
It's the other way around. You're right, Marcus. So 250 grams will be on top and 60.083 will be on the bottom. And you will divide that to get the moles.
Okay, go ahead. 250 divided by 60.083. What do you get?
I got 4.16.
4.16. What is this value would be?
I guess, so are we doing it as 4.2 instead?
No. Oh, okay. That's not okay. I'll do.
I think it's moles. It's 4.1.
Yeah, I said moles. MOL.
Mole of what? Silicon or silicon dioxide?
Ooh, wouldn't it be the silicon dioxide?
Okay, if I put the silicon dioxide, Brittany, the amount is given here as silicon.
Okay, so it'll be just silicone.
Fixed message from Matt.
Oh, wait, we actually did this question wrong. I think I see what we're doing wrong. So check it out. He asked specifically if we wanted to obtain 250 grams of silicon. So we're not looking at our whole 60.3 here.
Oh, it would just be silicone at the top then.
Right. So it's 28.085.
Step by step, because this question requires more than what you think. I want you to think about this question. Okay, go ahead, Marcus, first, and then I'll let Brittany can continue, or anyone can continue. The 200, I just want to give you one hint here. The 250 gram is for silicon, not for silicon dioxide, just let you know.
Okay, so silicon is only, one sec, what was that percentage we had for silicon? Silicon is 46.7.
Marcus, are you far away from your mic? I hear some echo, so can you your mic, please?
Okay, I'm not sure if this help. I just got one.
Now it's good. Now it's good. Okay.
Okay, great. So when we calculated earlier, we saw that silicon is 46.74% of amethyst. So for us to have 250 grams of silicon, we would need to have, let me see. I'm going at my calculator again. 250 grams divided by 0.4674 would give us 535 grams of amethyst.
That's the amount of silicon.
That's the amount of amethyst we would need to have 250 grams of silicon.
Okay.
So if we have 535 grams of amethyst, 46.74% of that.
535 comes.
I'm sorry?
Where does the 535 comes? When you divide 250 by 0.4673.
Right, exactly, 4674.
So what do you get?
535.
535 of what? What's this?
That is grams of amethyst.
Grams of amethyst, that's grams of SiO2.
Right, exactly. Because the question is asking if we want to obtain 250 grams of silicon, how much amethyst will we need? So what I did was I took our percentage of silicon, which is 46.74, and divided that by, took 250 and divided it by that percentage, which gives me the total amount of grams I would need of amethyst to have 46.74% silicon and make that 250 grams.
Okay. So you have 535 grams of silicon dioxide. That's called the amethyst.
Right.
Okay, so 250 grams of silicon divided by 0.4674 grams of Si gives you 535 grams of silicon dioxide. Is that what you said?
Exactly. And we can test that by taking the 535 and multiplying it times 0.4674, which gives us
535 multiplied by what?
0.4674. And that'll give us 250.059, which we would just round to 250, which means we have
what? Now, Marcus, let me help you out. You divide 250 by 0.4674 here, all right?
Right.
Then you do the same thing here. You multiply that, the same number.
Mm-hmm.
Do you see
oh,
that?
yeah, I would just join that to kind of show it by reversing it,
Okay, so
to show you that we got 250 grams of.
What's the number there? What's the number then? What's the number? 575 multiplied by 0.4674. What do you get?
250.059.
Okay.
I just rounded that to 250 though.
Okay, 250. Yeah, that 250. So that what is this? 250 grams
of silicon.
So that's the answer?
No, the answer is 535 grams. I was just doing that to reverse it to show you how I got that answer.
What's the final? My question is, what is the amount of amethyst according to your calculation?
535 grams of amethyst.
535 grams. Okay. Let me write that number because I see it in a different way, but I don't have the numbers by. I'll keep you this number. Then the answer might be right, but my approach is different. Okay. Is someone get the same number as Marcus? Is someone get the same number as Marcus for part C?
Hello,
Yes.
Professor.
Yes.
I wanted to find out if anybody can hear me because I've been talking, nobody's hearing me.
No, because I didn't. We didn't. Matt, I didn't hear you. I'm sorry, Matt. I didn't hear you.
Yeah, I think it's my computer.
Your computer. Okay. So, are you agree with Marcus or not? With his answer, with 535. I don't have the answer with me. That's why I need at least to get 3 people to come up with the same answer, and I'm going to explain my way. Maybe I may agree with Marcus or not. Marcus has 535. How about you, Matt?
I lost along the way and I came back in, so I'm confused. But I know you have to multiply with the Avogadro number.
I have to. Okay. Yeah. Okay. Write this down. Marcus, write this down. Everybody. So let me clean this up. What was the molar mass of silicon dioxide? It was what, 60 point what?
0.83 AMU.
The 60.083 AMU. In 60.083 AMU, you have 28.01 of silicon. Okay. If you have 250.0 grams of silicon, how much AMU, how much silicon dioxide you have? So my way is that I'm going to use a crisscross here. 250 times 60.083 divided by 28.01. Do that for me, please. And maybe Marcus would be right, or maybe I would be right. So let's do this calculation. If you get 535, then we both are right. But this is how the explanation would be. He has a different approach, but it's okay. It's okay. We all have different ways. But as far as the answer comes in the same, I would agree with that.
It's 536.3.
What's that?
It's 536.3.
Oh, that's good. So he's right. So he's right. I think it's a matter of significant figures that we do. So
yeah, Professor, if you didn't round up silicone, it would be 250 on the dot. 250,
but that was given.
No, so if I do it your way, if I do 250 times 60.083 divided by 28.085, I get 250 exact. I'm not getting the 530.
20.
You have, I think you have to like multiply and then you hit the equals and then you divide by 28.01. If you like do it all together, you're gonna get that 250. So you have to say 250 times 60.083, and then whatever the answer is, you divide by 28.01.
All right, yeah. So this time I got 534.83.
Oh yeah, what they're saying, Professor, is that you use different amounts of significant figures for the AMUs for silicon. You use 28.01 and I use 28.085.
That's what I use.
Right. So for us, we got 535, but it's not a big difference.
I got 536.
I'm sorry. So what? I'm sorry. So where are we now? But okay. I don't. You know, a matter of one decimal place. That's not the point. But the approach, the method of solving the problem is important for me. So I don't know. I just muted myself for a minute. So did you guys agree or what? What's going on?
When you simplify this problem, it's 536.26, blah, 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 blah. Yeah.
So obviously, I think Marcus also has a very close that I do have, but it's just a matter of rounding the numbers. But the concept, the question here says that here in 1 mole of silicon, In 1 mole of silicon dioxide, you have 1 mole of silicon. The proportion is 1:1, right? What's 1 mole of silicon? 1 mole of amethyst or silicon dioxide. That is about 60.083 grams of silicon dioxide. In 60.083 grams of silicon dioxide, you have 28.01 grams of silicon. That's the proportion. Now, if you have 250.0 grams of silicon, how much of the silicon dioxide you have? That's why the crisscross comes that. So X, which is the amount of silicon dioxide, would be 250.0 times 60.083 divided by 28.01. That's the right way. There's the way of thinking this question, the way of converting this question mathematically will looks like this. But you know, but the other would be like rounding up the number. But this is how we convert this problem into a mathematical equation. This is how it should be. Okay. So take the steps here. Like this is step A, this is step B, and this like a final step right here, step number C. You know, and we pretty much get anywhere between 535 to 536, depending on what numbers that you pick here. Okay, but it should be in 250 grams of silicon, you will have 535. So in 250 grams of silicon, to get 255 grams of silicon, you must have 535 grams of silicon dioxide. It makes sense, you know, because if you want to get 28 grams of silicon, okay, you need to have 60.018 grams of silicon dioxide. For 28, you need to have 60. So for 250, you must have 535. That's how the proportion goes. It's a conceptual question, actually, but you know, it's just comparing the amounts that makes a difference. All right. Okay, so think about this. If you have questions, maybe more, maybe we can bring to that the next class. But again, we have to go back with discussing with the empirical and molecular formulas. That's very important to discuss about empirical. So now we have to go back with calculating the empirical and molecular formula. In chapter 2, I gave you the definition. We gave you the definition about empirical formula and molecular formula. The empirical formula is the chemical formula with the smallest whole number ratio of atoms. Okay, we know that. We defined that in chapter 2. Molecular formula is the formula that represents the actual number of atoms. We also have structural formula here. Structural formula shows you how the atoms are connected to each other. This is definition, actually. For example, the molecular formula here is C2H6 because we have 2 carbon and 6 hydrogen. That's the molecular formula. The empirical formula is the smallest whole number ratio, which is CH3. Okay, so that was the definition. But now what we are trying to do is that we have to make quantitatively how we can able to calculate empirical formula and molecular formula. Okay, we provided definition in chapter 2, but in chapter 3 we are trying to determine the amount, how we can able to determine the amount. So let's see here. Okay, here, okay. I'm going to come back here, but I don't want to skip here. Let's just see something here. Benzene is made up of 6 carbon atoms and 6 hydrogen atoms. Okay, what is the molecular formula of benzene? Can somebody give me the answer? What is the molecular formula for benzene? Just reading here, what's the molecular formula for benzene?
6 carbon.
H6.
H6.
C6H6. What is the empirical formula for benzene?
CH.
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 CH. Very good. Determine the percent composition of benzene from its molecular formula. Okay. Determine the percent composition of benzene from its molecular formula. Determine the percent composition of benzene from its empirical formula. Okay, I'll give you each 2 minutes or 3 minutes. I want you to determine the percent composition of benzene from its molecular formula. This is MF. I use MF. This is empirical formula. I use EF. Okay, EF stands for empirical formula. MF stands for molecular formula. Okay, let's go ahead and determine the percent composition of benzene from its molecular formula first.
Quick question though, isn't it going to be the same?
No, it's not going to be the same.
I mean, the percent composition from the molecular formula and the empirical formula, the percentages never change.
I don't think so, Marcus. We have to make calculation.
Okay.
We have to make, I don't think so. I don't think so. Remember that we're going to determine from the perspective point of molecular formula here. This one is from the empirical formula. You see, I don't have the answer, but we can see. But I'll tell you my intuition now. I don't think so. It's going to be the same. But let's try. Let's first try. If someone wants us to get the answer or lead how we get the answer, let me know, okay? But I need everyone to try first, and then we can go from there. If anybody wants to try with this question, with the first one, please let me know. Okay.
All right, I'll do it.
Yeah, go ahead, sir. Marcus, go ahead.
Yes, sir. So benzene is made up of carbon and hydrogen. The first thing we're going to do is find out the molar mass. So for 6 carbon and 6 hydrogen. Carbon has a molar mass, the AMU for carbon is 12.011.
Okay.
So we have to multiply that times 6.
Okay.
So for this, we're just using 0, 1, right? We're just using 4 significant figures.
0, 1 would be fine, yeah. So I'll put confusion, yes. Yeah, I'll go with 12.01, yeah.
All right, got you. Then for hydrogen, we got 1.008. And we have to multiply it times 6.
Okay.
So let me get my calculator.
Okay, 6. Okay, go ahead. 6 times 12.01. What do you get then?
72.06.
Okay, that's for carbon.
Right. And for hydrogen, 1.008 times 6, 6.048.
6.048. 48. Okay. So when you add, which is C6H6, that gives you, what do you get? 72.06 plus 6.048.
It gives us 78.10, we'll call it 78.11.
78 point what?
11.
Okay, AMU. Okay, that's the molecular mass. That's the molecular mass for C6H6.
Right. And now the question is asking us for the percent composition.
Yeah.
So
you do for carbon, okay.
Carbon is going to be 72.06 divided by 78.11. So carbon is 92.25%.
Sorry?
92.25%.
92.25%, okay. So what's the percent of hydrogen?
Okay, that's going to be 6.048 divided by 78.11. So that gives us 7.74%.
7.7?
7.74.
Okay. Okay, we have the answer here, which is given by Marcus, 92.25 for the percentage for carbon, for the percentage of hydrogen, 7.74.
Right. That adds up to 99.99 instead of 100, but that's just because of the significant figures.
That's almost 100%. That's a proof. That's a quality control. You can add them up. If you came up with 99.99, almost 100%, so the answer is correct, you know? that at least you don't have any foreign substance contaminated there. That's how qualitative chemistry would help. Any question with Marcus' explanation here? Any question before we go part B? Okay, I'm pretty much sure everybody gets this. So, okay. So if there's any question, please go ahead and ask, okay? So we have determined the percent composition of benzene from this empirical formula. We're going to follow the same step, the same way. The only thing is that we're going to use as a molecular weight CH this time, because that is the empirical formula. So that's going to be approximately 12.01 plus 1.008. I don't know if you can calculate this. What do you get, guys? 12.01 plus 1.008. 13 point,
13.018.
13 point what?
018.
018. Okay. So this way we can able to calculate the percent of carbon would be like 12 over 13.018. 500. Okay. The percent of hydrogen is going to be 1.008 divided by 13.018. That's how
much consistency. I use 12.01 for my carbon and divide that by 13.018.
Yes.
And that gets me 92.25% again.
Okay. 92.25. Okay. Which is the same as the previous number, right?
Right, because mathematically that's really the only option.
Yeah, because it's a proportion. Yeah, it's true. It's true. So you get, I believe you get 7.74 for hydrogen. If you divide one, what do you get? 1 divided by 13.018. What do you get? 1 divided by 13.018.
008 divided by 13.018. I get 7.74%.
That shows you that the actual empirical formula for benzene is CA. Because here is the point. The point is that to determine the molecular formula, you must start with the empirical formula. Because why is that important? The empirical formula is like when you build a house, you have to have a foundation, right? The empirical formula is a foundation for the molecular formula. So the proportion has to be the same. And then you go to the next step. You get to the actual number of atoms of molecule. So if the base is a great foundation, then you get the actual number of atoms in the formula. So that's how we get that number. So yes, it makes sense. That's a proof that CH is the actual empirical formula for C6H6, which is the molecular formula for benzene. Good. Okay. Now let's go back to how we can able to determine empirical formula by using a quantitative analysis. Okay. So we may have here, let's see, we may have here a question or example. A sample of black mineral is called hematite, which is an oxide of iron found in many iron ores, contain 34.97 grams of iron and 15.03 grams of oxygen. Based on this, what is the empirical formula for hematite? Okay, so we get this question is already done here on the next slide, so we can able to follow the slide here. So we have always, when you do a problem like this, you have to write what's given. That's very important. What's given to you? You'll be given 34.97 grams of iron. You'll be given 15.03 grams of oxygen. From this given value, you need to determine, what's required is to determine the empirical formula. So in this case, you also have been given to okay, I mean, I got your text now. I'll take, thanks for letting me know. I'll take a point here. I'll write down that. Thank you. Thank you for letting me know, Marlene. I don't know if you are still here or not, but I see your text. Also, it's given that iron is 55.85 grams and oxygen has 15.994 grams. That's given also. Okay. So from this given value here, we are trying to determine the empirical, we are trying to determine the molecular, you're welcome, Marlene. We are trying to determine the empirical formula. So please watch the steps. The steps are very important. The first thing that you need to do is you need to convert the grams to moles. So what they did here, 34.97 grams of iron, change into moles. You have to divide that. We learned that in chapter 1. You have to divide that by 55.85. That's the mass of the molar mass of iron. It's the same way we do for oxygen. We divide 15.03 grams of oxygen, which is given, convert that into mole, we divide that by 15.994. Okay? So we got two more ratios, 0.6261 mole and 0.9396 mole. So we got two ratios here. One mole for iron, but 1.5 moles for oxygen. So in this case, this is the thing that I want you to pay attention. You cannot round numbers like 1.5 to the next number. Because the numbers that you used has to be integer, okay? And they have to be, there is a restriction. There is a restriction of rounding numbers. If a number like 1.5 or 1.6 or 1.7, they cannot be rounded. If, when you divide by the smallest whole number ratio, and if you get 1.9, that's rounded to 2. Or if it is like 1.1, it can be rounded to 1, okay? But something like 1.5 is in the middle of 1 and 2. So in a situation like this, you need to find another integer, smallest integer, and multiply the moles by the same integer. They did here, they multiply here by 2. To make the second number into whole number, into integers, you see 2 and 3. Okay, so that number is used as a subscript to write the formula, which is Fe2O3. See, if 2 doesn't bring the mole ratio into a whole number, then you may have to try another number, maybe 3, maybe 4, you know. But in this case, we are lucky. The number 2 works everything. The number 2 helps us to multiply both, and then we get 2 and 3, we get Fe2O3. Fe2O3 is actually, if you Google right now, hematite is the mineral name. That is the mineral name of hematite has a chemical formula Fe2O3, which is, what's the name of this compound? The nomenclature for Fe2O3, by the way. We learned that in chapter 2. Hematite is its mineral name, but its chemical name. What's the chemical name? Fe2O3. What's the name of Fe2O3? We learned that in chapter 2.
Is it iron trioxide?
No.
Iron oxide.
No.
Iron 2 oxide.
No.
Iron 3 oxide.
Iron 3 oxide. So 3 actually comes from iron. So we need to learn about how to name compounds. I have a video posted in the announcement section. Please watch them. That's the nomenclature video, nomenclature. Please watch that video. Also, I want you also to watch to also go back with reading the PowerPoint in chapter 2, especially when transition metals involved with Roman numerals, with the actual number of Roman numerals. So the 3 actually comes from iron, the 2 comes from oxygen. Always oxygen has a -2 charge, it's in group 6, but iron has a +3 charge. So we have to indicate iron 3, Roman numeral 3 oxide. So that's how we determine the empirical formula. This is the empirical formula because this cannot be broken down. Okay, Fe2O3 cannot be broken down further because that's the smallest whole number ratio. So we call this empirical formula. So here is another step that we also need to learn. Slide number 26.
Professor,
I'm sorry?
I did not understand where you got the 2 and 3. Understand?
The 2 and 3, okay, I have to go back here. Okay, here is Matt. Here is the explanation. We have been given 34.97 grams of iron, 15.03 grams of oxygen, and then we are interested to determine the empirical formula. So the first thing that we did was converting the gram value into moles. So we got 0.6261 mole for iron. We got 0.9395 moles for oxygen. And now the next step is that which one is the smallest mole ratio with the iron and oxygen? The smallest one is 0.6261. So we divide every mole ratio by 0.6261, 0.6261. So we got 1 for iron, we got 1.5 for oxygen. So this number, 1.5, cannot be used to write a subscript because this number cannot be used as a subscript because it's not integer, it's not whole number, it's a decimal number. So you have to come up with a number that can convert both mole ratio into whole number. So we multiply this by 2 to get an integer. So when we multiply 1 by 2, we get 2. When you multiply 1.5 by 2, you get 3. That's how 2 and 3 comes from. The important thing that mathematically, if you multiply a ratio by constant number, okay, the result doesn't change. It's 2 and 3. Okay, why we pick 2? It's random number. You know, you can pick 3, you can pick 4, you can pick 5. But remember that the numbers that you multiplied can bring both ratios, both mole ratio into integer, so that the 2 and the 3 can be used to write a formula. So that's why we use 2 for iron, we use 3 for oxygen. Okay, so maybe that, Matt, does that make sense?
Yes, Professor. Thank you.
You're welcome. Okay. So here is also a sketch for you. Actually, this sketch would be really a good GPS to understand how we came up with if the mass of 2 will be given, converting mass to moles divided by the lowest mole ratio, and then convert the ratio to the lowest whole number. And then finally, you came up with empirical formula. So like this is like step A, this is like step B for determining the empirical formula. This is like a good guideline or GPS. So that here you need to determine the number of moles for each atoms. We did this here. Divide the number of moles by the smallest number. Actually, that's here. This is for this is number 1. This is for number 2. If necessarily, multiply by an integer value so that all the values end up as a whole number. So you have to multiply by this by an integer value. When we say integer value, it can be 2, it can be 3, to end it up as a whole number. So a whole number is the one that is used as a subscript to write the empirical formula. Okay, a whole number is the one that's exactly slide number 24. Slide number 24 would be a good reflection of slide number 25. Okay, so I want you to compare. If you want to understand this slide number 25, look for slide number 24. Slide number 24. It will really gives you a guideline, a great guideline. So here here is also another thing which I want you to also understand, that when you need to multiply numbers, when you do the Moore ratio, right? When you do a Moore ratio, like let's say when you do a Moore ratio, you get 2.04. That you don't have to multiply by an integer. It's like 2. If you get 3.98, you can round it to 4. If you get 2.95, you can round it by 3. You can. This is very much close to 3. But if you get 2.5, 1.33, 3.25, 1.20, 3.80, 2.75, they're not something that you can round it up. You have to find a number multiplied by an integer value in order to get a whole number. So this is a practice for everybody. So like, for example, let me give you an example. I have 2.50. If I want to change 2.50 into whole number, what number should I use? What integer should I use to make, what the smallest number? Remember, the smallest whole number is the smallest integer I'm going to use to convert 2.50 is going to be, what do you think? 2. Yes, Shannon. Shannon, I read your text. Thank you, Shannon. That's 2. Yeah. 2.50 has to be multiplied by 2. It gives me 5. All right. So this is something, this is not, this is like a trial and error method. There's no formula for this. Like, for example, you have one, when you divide 2 more ratio, you ended up with 1.33. This number cannot be written or cannot be used as a subscript. So you must think, oh, should I multiply 1.33 by 2 or by 3 or by 4 to get a whole number? What do you think? 1.33. What numbers bring 1.33 into whole number? You text me if you want to. What's that?
3.
3. When you multiply that, what do you get? 1.33 by 3.
So you get 3.99.
Very good. 3.99. So that's 3. 3.99 can be rounded to 4. Excellent. Good. So 3 would be the small integer.
But can I also use 2, Professor?
2.
Can I also use 2 to multiply? Because it's going to give me 2.
What do you get when you multiply 2?
It's going to give me 2.66.
You cannot do that. You cannot do that. 2.66 is not a good number. You cannot round it. To write empirical formula math, is that math?
Yeah.
You cannot do that. I have my cell phone right now. I multiply 1.33 by 2. I get 2.66. You see math here, the list. Do you see that? The only numbers that you can round it is like if you get 2.04, that can be 2, 3.98, that can be 4, 2.95, that can be 3. But 2.66 needs.
Wouldn't that remain 2.7 and you still couldn't round it up?
Again, no. No, because the formula that we need to determine must be known. And then remember that you multiply the number, the integer, if you have 2 elements, you multiply those like 3 for the 2 moles. So if you have A and B, right? If you multiply A and B by the same number, let's say K, you multiply by the same constant number, you get AK and BK. It's the same. The value of A and B is not going to be changed because you multiply by the same constant value. So 1.33, like let's say if oxygen is 1.33 and iron is, I don't know, like 2.33. So you multiply by 3 and you multiply by 3, you don't change anything. You multiply both of them by the same constant number. The goal is to convert the decimal number into an integer, okay? So you have to think that when we determine empirical formula, when are we rounded up, or when are we find an integer to convert them into whole number. Something like this here on the left, they can be rounded up, but this 3.25, 1.20, 3.8 even, now it cannot be rounded. You need to find a number to multiply with to convert 3.80 into an integer.
Wait, Professor, so you said 3.8 cannot be rounded up.
For determining empirical formula cannot be rounded up, yes.
Okay, thank you.
You're welcome. So like, for example, we have 3.25. What do you have to do with 3.25? Find that you can multiply with, and then we can able to convert that into a whole number.
It's gonna be 3, right?
I'm sorry?
3.3.
3.0.
3.3?
Yeah.
Well, 3 plus 3.
I multiplied that by 4.
No, but
You said to the nearest whole, right? It's a whole number. I don't think there's gonna be any point in there. So it's gonna be
25 multiplied by what's the numbers that you said?
I said 4.
4.
Okay, hold on. Just give me a second. Multiplied by 4. That's 13. And now let me ask you this. Is there a number less than 4 that converts 3.25 into whole number? Like 2?
No.
No? 3.25. Can you multiply 3.25 by 3? Okay, yeah, you're right. 9.75.
That gives 9.75.
So what is 3.25 by 2? Okay.
6.5.
Okay, Marcus, I got it. Okay. Okay, you're right. Who said 4?
The whole class.
Okay, that's
Me.
That's right. Thank you. 4. 4 is the only number that can convert 3.25 into whole number. Okay. Okay. Go ahead with 1.20.
5.
5.
Okay, Marlene. What's up? 1.20 by
5.
5.
What do you get?
That's gonna give us, what is it? 6? Yeah, 6.
Okay. Okay. So a number less than 5 cannot bring 1.20 into whole number, integer, right?
Right.
Okay. How about 3.8?
5.
What do you get when you multiply?
19.
19. Okay. No number less than 5 cannot change 3.8 into whole number.
I agree with that.
I mean, if you try 4, if you try 3, have you tried that?
Yes, and they all give you decimals.
Decimals. Okay. Okay. Wonderful. Okay. How about 2.75?
4.
Oh,
What numbers that you get?
And it gives you 11.
11.
Okay, excellent. So you see, this is how we pick numbers. We have to try the smallest numbers that we're going to start with 2, and then 3, and then 4, and then 5. It goes on, okay? So please look on the restriction here. When these are numbers that you can feel comfortable to round it up, but the numbers like this, you have to find a whole number. You have to find an integer to multiply with. Okay. We're going to continue. In the meantime, please slide number for Thursday. I mean, today's Thursday. I want you to look for this example here. Okay, I want you to look for this example and calculate this example, and then once you are practicing to calculate the empirical formula, I want you to look slide number 13 to determine the molecular formula. So 27 and 30 would be your practical work for next week, so that we can able to continue with that.